Okay, so let us discuss about eigenvalue and eigenvectors. I told you that you have a square matrix A. Suppose you have a square matrix A. A is a square matrix. Okay, maybe, yeah. A is a square matrix. A is a square matrix. Suppose A is a square matrix of size n cross n, right? Then we saw that when you multiply A with a vector x, this resultant quantity becomes a vector, fine. But it might happen that for special vectors, x bar, you can have ax bar is equal to lambda x bar. What does it mean? It tells us that ax bar, this is a vector, and x bar are parallel, first of all. Then second is the length, the magnitude ax vector got scaled via a factor lambda. Okay. So this special x bar for which ax equals to lambda x happens is known as an eigenvector, and corresponding corresponding to corresponding to the eigenvector x we get a constant that is lambda. So that is a scaling factor, and this is actually the German word they have assigned to the scaling factor. This is what they call is eigenvalue. All right, this is what they call as eigenvalue. Fine with you, right? Okay, so this is what the motivation about eigenvalue. Eigen is a German word, and it means that this is the scaling factor. It is not the full, it is the it's some part of the full quantity. That's what is known as eigenvalue. Can you see, if I want to motivate regarding this, we can take this we can take this x vector over here and y vector over here, and we have this vector x here. Okay, now what I claim is, when you multiply the vector x to this matrix A, the resultant vector will be parallel to this x bar. That means on the same direction, but it can be less than the magnitude of x bar, which is this case. But it can be also that it can be increased in magnitude like this one also, isn't it? It can be both ways, right? When lambda is less than 1, you represent the red case, right? When lambda is greater than 1, that means it is more than x. The length is more than x. If lambda is greater than 1, the length of ax is more than x, right? So therefore it will go away from the x vector pointing, right? So this one, the red one, is for lambda less than 1, when you have mod lambda less than 1. The orange one is for the case when you have mod lambda greater than 1. Okay, real eigenvalues, real, I'm saying. Now it can be also possible that you have this x vector of x and y here, you have this x vector over here, fine. Now another case is possible that when you multiply a vector into x, it can go to the opposite sign. This can be ax. So you can say this is minus 0.5x. Ax equals to minus 0.5x. Then it can be on the opposite side, 180 degrees, right? Can you see the geometric interpretation of all this? It can see now also these are parallel. Even they are but we say this to be anti-parallel. Yes. The first case is a very simple case, but the third case, the second case I drew here, ax was anti-parallel to x. The angle between them is 180 degrees. Why it happened? Because you multiplied with a negative quantity, minus 0.5. So that minus 0.5 is known as the eigenvalue through which it got scaled. Okay, fine. All right. Okay. First of all, I'm finding it a bit difficult in pointing out my arrow. Okay. Okay, let's see. So what I'm telling you is you had this x vector on the 2D plane denoted by orange arrow. Can you see that? So this is the x vector, right? Now I'm asking you what happens if you multiply a matrix A to it, that is Ax bar, okay? Now I told you that it can be on the same direction, which is denoted by the first case A, right? It can be on the same direction when mod lambda is less than 1 or lambda is less than 1, okay? Or lambda greater than 1, it will go more ahead, right? Now if lambda is negative, what you will do? If lambda is negative, it will be first of all Ax equals to minus 0.5x, right? So it has to be on the same direction as x. It has to be parallel actually. It has to be parallel. But it is on the negative direction, right? So therefore it is exactly in the same way, same direction of the vector, but it is pointed in a opposite direction. So you can see Ax is now 0 - 0.5x. It is pointing totally away from it. But the quantity is less. It is scaled by 0.5. So you can carefully say that this length in blue is half the length in orange. Can you say it? Because it is scaling by 0.5, half. Fine? Clear? One other is, I need this here. It will come. Yeah. Is it happening? Are you able to hear? Yeah. Okay, so this is the concept of eigenvalue and eigenvectors. Hmm? Now let us try to compute an eigenvalue and eigenvector for a matrix, so that we will know what we want to do here, and then we will resort to numerical methods. Okay, so I ask that take this matrix A. It's just a simple 2 by 2 matrix, 7 3 6 4. Okay, for this matrix I want you find eigenvalues. Find eigenvalues and eigenvectors. Okay. So how you find eigenvalues? Of course, Ax equals to lambda x you will have. Then you take lambda x from the left hand side. Fine. Okay. If you want to group it, you can multiply like this equal to 0. From this you can say there is a theorem for this, that in order to have this unique solution, you need determinant of A minus lambda I to be 0. This is a theorem which I am not telling you about. Okay, but from this you can straightforwardly get this determinant of A minus lambda is 0. Now I ask you to solve that. What is A minus lambda I? What is A minus lambda I? What is A minus lambda I? Can you tell? A minus lambda I will be another matrix, isn't it? Yes. So you just subtract lambda in the diagonal entries. Yes. So this will be the matrix A minus lambda I. Now I am interested in taking the determinant. Determinant of A minus lambda is equal to 0. So what we will get? Determinant of this quantity, 7 minus lambda, 3, 6, 4 minus lambda. This is equals to 0. Okay. So can you solve this? What it will be? Multiply this one first minus the cross one. So 7 minus lambda into 4 minus lambda minus 6 into 3 equal to 0. Can you solve for lambda now? Lambda equals to what? Yes? Anyone? Okay, great. So as you said, the values are 1 and 10. Okay. So you can see from this we get lambda equals to 1 and another lambda 2. Lambda 1 is 1 and another lambda 2 is 10. Okay. Fine. Now, which one is the greatest one? Which one is the greatest one? Out of lambda 1 equals to 1 and lambda 2 equals to 10, I am asking you which one is the greatest eigenvalue? Yes, that is has more value. So lambda 2 equals to 10 is the greatest eigenvalue, and that's what we call it as a dominant eigenvalue. Dominant eigenvalue. Okay, fine with you? Okay, let us move. Now that you know that lambda 1 equals to 1 and lambda 2 equals to 10 are the eigenvalues. Now, can you find the corresponding eigenvectors? Your job now is to find the corresponding eigenvectors to these eigenvalues. Can you find the corresponding eigenvectors? So for that, you have to just do a minus lambda 1 I into x vector is equal to 0 vector, right? What is a? Can someone tell me? 7364. Okay. Minus lambda, suppose lambda 1 we will take 1001. Okay. And you multiply. Sorry, my handwriting is not that good today. Change of my tablet. Okay. So what we are getting? We are getting 6363. Suppose vector x1, x vector you can write is x1 and x2. So what you have from here, 6x1 plus 3x2 is equals to 0. So you can write 2x1 plus x2 equals to 0. Right? So can you tell me what we get here? So you can get here x1 is equals to minus half x2. So how your vector looks like eigenvector? Your eigenvector will look like x bar, that is equals to x1, x2, and this is equals to x1 is half. Maybe it is better to write x1. Okay, what is x2? Minus 2x1. Right? Fine. From here we can get this. X2 equals to minus 2x1. So you can take x1 as common and 1 minus 2. X1 can be any real number. X1 can be any real number. X1 is the freedom case now. X1 can be any real number. Right? Yes. Now, from this example, you can appreciate that eigenvectors are not unique. Right? Eigenvectors are not unique. What are the eigenvectors? Can you say? One eigenvector is 1 minus 2 because I multiplied 1 with this. Another eigenvector can be 2 into 1 minus 2. Anyone can suggest another eigenvector. Minus 1 of 1 minus 2. All these are eigenvectors. All these are corresponding eigenvectors to that eigenvalue. Okay. So eigenvector is not unique. Okay. If let me write this here. Yeah. What I meant is if x bar is an eigenvector, if x bar is an eigenvector, then alpha x bar is also an eigenvector. That's what we saw, right? We got the eigenvector to be x1 multiplied by 1 into minus 2 vector. X1 can be any real number. So therefore, you can have infinitely many eigenvectors. Okay. So therefore, if x is an eigenvector, alpha times x, if alpha is a constant, is another eigenvector. Alpha can be any real number. And these are eigenvectors corresponding to which eigenvalue? Lambda 1. Okay. Because we are solving it for lambda 1. So these eigenvectors which you are getting are the eigenvectors corresponding to lambda 1 eigenvalue. Okay. Now, finding eigenvectors for lambda 2 eigenvalue is missing, isn't it? Can you try that? Can you try that? Now, lambda 2 equals to 10, right? Yes. So, what is the corresponding eigenvector for this? What is the corresponding eigenvector? So again, you can solve a minus lambda 2i, lambda 2i, a minus lambda 2i x2 is equal to 0 bar. Can you solve and tell me what is x2 you are getting? Like what is, yeah, what is x2? That means maybe I should write it in a different notation. Maybe let me write it as v2. Okay, v2, just to because x2 we already used in the previous page. So v2 equals to what? New one corresponding to 10 eigenvalue. Hmm? Huh? No, v2 is a vector. V2 is a vector. You have to tell me what are the components of the vector you are taking. Okay, some constant beta and you are saying 1, 1. Yes. So yeah, you have to tell in a better way. Okay. Notations and all in this course are very much important. Okay. And the wordings in this course are very much important. Okay. So V2 vector you can find to be beta any linear any real number times 1, 1 vector. Okay. Right? Fine with you till now? Okay. So can you see that V1 vector can be written as, sorry, the X1 vector which we found in previous page is what? Can you tell me what is X1? We had 1 minus 2, right? Yes, X1 vector is 1 minus 2 and V2 vector is 1, 1. Like these are two vectors I chose. You can also multiply any scalar and get another eigenvector, it's fine. But these are the two eigenvectors, okay? Now, usually, we are much more interested. We are more interested. We are more interested in eigenvectors, in eigenvectors of unit magnitude. Okay, of unit magnitude. Fine. What do you mean unit magnitude? That means the vector should have unit length. If x bar is a unit vector, x bar is a unit vector. Okay, x bar is said to be a unit vector if the norm or the magnitude of x is equal to 1. Okay, so what I ask is v2 equals to 1, 1. Okay, v2 equals to 1, 1. This is this a unit vector? No. Is this a unit vector? No. Why? Because if you take the norm of v2, what is it? It is square root of 1 square plus 1 square, the unit terms. That it is root 2. Okay. So if you want to convert this vector to a unit vector, what you should do? What you should do? Just divide by the norm. Just divide the vector by the norm. So when you take the magnitude of that vector, it will be divided by the norm and the magnitude will be 1. Okay. So what I mean is if you want to convert, now we know vector. If you want a unit vector, what you should do? Let us write it to be n2. n2 vector is the unit vector. How you will write n2? n2 equals to 1 by 1 divided by the norm of v2 times v2 vector. So it will be just 1 by root over 2 which you got before. Okay, so it is just yes. So can you compute the norm of n2 now? So norm of n2 is equals to root over of 1 by root 2 square plus 1 over root 2 square. That is equal to 1, isn't it? So that like this you can create a unit vector if you just have a vector. Just divide the vector. If you divide 3 by 3, it will be 1. That's the idea. Why it works? Why when you divide 3 by 3, it is 1? Because 3 is the magnitude and you are dividing by the magnitude itself. So therefore it is 1. Fine. Any doubts? Any queries? Any queries? Okay, fine. Okay, so now you learned What is an eigenvalue? What is an eigenvector? Now for a 2 by 2 matrix, this was very nice. For a 2 by 2 matrix, this was very nice. But if your matrix goes 3 by 3, okay, it is nice. Because at least a cubic equation you can have. But most importantly, I think I forgot to tell you, when you solve for eigenvalue like this, when you compute the determinant of a minus lambda equals to 0, this is something special. This is known as a characteristic polynomial. Because finally you will get a polynomial in lambda, isn't it? So this is known as a characteristic polynomial. We denote it by p of lambda is equals to determinant of a minus lambda I equals to 0. Okay. This p of lambda will be a polynomial. When you solve this determinant, you will get a polynomial in lambda. That is, it will be of the form, say a naught lambda to the power n, or here square plus a1 lambda plus a2 equal to 0. Okay, and you have to just solve it, isn't it? So here you got that this is a characteristic equation which you did not notice it. So this is a characteristic equation. Okay. This is a characteristic equation. Can you appreciate that this is a quadratic equation? This is a quadratic equation, isn't it? Is this a quadratic equation? Yes, this is a quadratic equation. Okay. So therefore you can imagine that when you solve determinant of a minus lambda equals to 0, you are actually solving a polynomial equation. Okay. If you have a 2 by 2 matrix, this polynomial equation is just a second order polynomial, quadratic equation. Now, if you have a 3 cross 3 matrix, it will be a cubic equation. If you have 4 by 4 matrix, quartic polynomial. 5 by 5 matrix, quintic polynomial. Okay. 6 by 6 matrix. This is, you know that the complexity increases as you increase the size of the matrix. Okay. So therefore, this is the idea. In order to convey to you the idea of eigenvalues and eigenvectors, we have taken a simplest matrix 2 by 2. But what happens? Large matrices. Large matrices are bound for you because you will have to work with big data. Okay, big data techniques. Okay, so if you have big data, that means you will of course store those data in a matrix. There is no other way. Okay, so if you encounter a big matrix, and of course you need to compute the eigenvalues. Why you need to compute eigenvalues? Because you want to reduce the dimensionality of the data using principal component analysis. Yes. So now you need to find eigenvalues to find the best feature. So how you compute the eigenvalues if you have a large matrix? Now can you understand the question I am landing at? For a 2 by 2 matrix, you can compute the eigenvalues, but if your matrix size gets larger, computing eigenvalues numerically tends to be very hard. Therefore, there needs to be devised numerical methods which can compute the eigenvalues. And in order motivated, we will learn the two methods. Okay. Now I told you the dominant eigenvalue is 10 here. I will tell you one method which can compute the dominant eigenvalue only. No other eigenvalues, only dominated eigenvalues. And since only one eigenvalue you are getting, which is not of much help to you, then you need to find a method which can compute all eigenvalues for you. And that is another method known as QR method. That's the job for today's class. Okay. That's the job for today's class. Right. So let us see the next method for here. The power method, where we can find the dominant eigenvalue. Okay. Now what is the power method? Okay. So let us see. Let us see the power method here. Okay. All right. So suppose you have a matrix A. Okay, suppose you have a matrix A and you have to find the eigenvalues of the matrix, right? So as I told you in the beginning of the class, why the name is power method? The name is power method because in the process of this method, you will compute the powers of the matrices, and you will see computing powers of the matrices helps you in finding the eigenvalue. Okay, that's the idea. Let us see. Consider a matrix A. Okay, consider a matrix enough. Is this enough? Can you compute eigenvalue of a rectangular matrix? No. So if I write consider a matrix A, that it means itself that it is a square matrix. That is the number of rows and the number of columns are equal. Okay, consider a matrix A that is a square matrix. Okay, and suppose the eigenvalues for this matrix A are lambda 1, lambda 2, so on up to lambda n. Okay, there are n eigenvalues because it's an n by n matrix. There are n eigenvalues and correspondingly there are n eigenvectors v1, v2 up to vn, right? These are the eigenvectors. Now the question is, you need an assumption. You need an assumption for this method. The assumption is one of the eigenvalue should be greater than other eigenvalues. Suppose assume that lambda 1, okay, mod lambda 1 is greater than lambda i's for all i's equals to 2, 3 up to n. Okay, this is the assumption. Don't worry about this, else you might think like how this can be always true. Okay, like think that lambda 1 is just an eigenvalue. Okay, suppose you have eigenvalues 1, 3, 6, 8, 7. Okay, which one you should make lambda 1? 8, isn't it? 8 is the largest eigenvalue, so make 8 to be lambda 1. Arrange in such a way that this is fulfilled. So you can say lambda 1 is 8 in my case, and therefore this will be fulfilled, isn't it? Can you see that this is fulfilled? Lambda 1 mod is greater than all eigenvalues mod, right? Good. So therefore this is known as the dominant eigenvalue. If this happens, lambda 1 is known as the dominant eigenvalue. Okay, fine. Now our idea is how to compute this lambda 1, how to find lambda 1. This is the job of this method. Okay, I told you, it will find the dominant eigenvalue. Now I'm asking you how it can find the dominant eigenvalue. Any thoughts? Any ideas? Any ideas? Any ideas? See, it is a numerical method. Power method is a numerical method, right? So, always at the start of the numerical method, what we ask? Yes, we ask for an initial guess, right? So here it also we will ask for an initial guess. Okay. So we ask what is the initial guess? So here instead of a number, we will have a vector. Previously in all methods, you were having numbers. So now this case we will be having vectors. Okay. So suppose V naught is the initial vector, initial guess vector to start our method with. Okay. Now what we do is very straightforward method, nothing hard. Okay. You will see how this method is simple. This works like magic. This works like a magic. So what you do, you take this initial vector a v naught and then you do this, multiply this with a matrix, a v naught. Okay. A v naught. Fine. So it will be another vector. Multiplying, I told you this mantra, right? Multiplying a vector with a matrix is giving you a vector. If you remember this keyword, then half of your job is done. Okay, so if you have v naught a vector, when you multiply a matrix A to v naught, it is again another vector. It is again another vector. Okay. Now I ask you, if you do a to v naught, it is going to be another vector. Okay. So we keep on multiplying the matrix A to this sequence of multiplications. Okay. Fine. But the idea is you have this iteration scheme. Now you should ask, we took an initial guess for a numerical method, right? But what should be our iteration scheme? Our iteration scheme is the most important one because it lands us to the solution. Okay, what is our iteration scheme in this? I never wrote this. The iteration scheme for our method is the new vector, that is, suppose at k plus 1th step, the new vector you will take will be equal to a matrix, sorry, yes, a matrix multiplied with the vector vk. Okay, can you see? You are predicting the future vector depending on the past vector. The same technique applied as before, predicting the future based on the last value, predicting the future based on the past. Okay, so I ask you, you had a v naught. How you compute v1? V naught is the initial vector. V naught is the initial vector. Now I ask you, what is your next vector? Yes, that is V1, right? V1, according to this scheme, is a V naught. What is V2? It will depend on the previous past. That will be a V1. What is Vk? A Vk minus 1, right? So like that, you have to try new vectors. But what are we doing here? What are we doing here? Can you analyze what are we doing here? We are creating new vectors. We are creating new vectors v0, v1. V0 is our new initial guess. We created vector v, right, by multiplying a with v0. Fine. We created then vector v2. We then next created v3, v4, v5, so on. That's what we are doing so far. Yes, you will be amazed to see. You will be amazed to see that after some iteration, it converges to a specific vector. Okay, what is that vector? Can you analyze now? See, you now know the method. You now know the power method. You took a vector, any initial guess vector, multiplied with A, got a new vector, multiplied with A again, got another new vector, so on. Now I am asking you, can you see what is happening? Just think what we have done right now. Think what new thing we will get if we do this. I want you to think. Just spend a few minutes thinking. Just think like geometrically also you may think. Hmm? How? We don't know like if you have v naught, then you multiply a into v naught. This is a v1 you will get, this is v1 you will get. Okay, then if v2 you will get, but where this v1 v2 will be oriented, we don't know. Whether it can be parallel or it can be scaled or rotated, we don't know. How? Any ideas? The idea is when you do this, what we are doing here, we are getting new vectors, right? We started with some initial. Hmm. Control Alt Shift H. Okay. So yeah, what are we doing right now? Yes. What are we doing in this method? Can you please help us explain? Huh? Huh? So what are we doing in the next previous slide? What we did? The next one? Huh? What we did? What we did in the past slide? Can you predict the future? What is going to happen? Depending on the past, predict the future. Predict this slide, what I'm going to write. You should come there. There last. So what we are doing here is we started with the initial vector, right? V naught. Then what we created V1, right? We created V1 as A into V naught. Then we created new vector A2, sorry, V2, that is A into V1, so on. So if you go on like this, you will reach to another vector Vk plus 1 is a Vk, right? You will go like this. By doing like this, you will be amazed to see that Vk is converging to the eigenvector. Vk will be converging to the eigenvector of the matrix. Okay, eigenvector of the matrix. Now, the idea is you have the eigenvector, but what you were after is on the eigenvalue, right? You wanted eigenvalue, but you got eigenvector. Now, this is the eigenvector. Can you tell me how using this eigenvector you can find eigenvalue? Can you tell me? So I told you a concept. I told you a concept of unit vector, right? Unit vector. Yes. So Vk is an eigenvector, but it doesn't mean necessarily that it will be a unit vector, right? It will have some magnitude. It will have some magnitude. First of all, we will do a unit vector transformation, but I will not tell you why because it might be confusing, right? But what I will tell you, we will see that later. So Vk is an eigenvector. What does it mean? When you multiply it with a vector with the matrix A, it will return lambda into that eigenvector. Vk equals to lambda into Vk. Fine. Now from this, how can we extract lambda? We don't, if we can solve determinant, we can solve the determinant, but we don't want to do it because it will be taking a lot of time if your matrix is large. Okay. So what can we do next? What we can do is just take the dot product. This is a vector on both sides, right? We can take a dot product with a vector. So what I will do is a vk, I multiply with another vector vk, lambda vk dot vk. Fine. Dot product will give you scalar, isn't it? Dot product will give you scalar, right? Previously we had a vector. Okay, previously we had a vector. Now we are dealing with scalar after you took a dot product, right? So now can you write lambda as a vk dot vk by vk dot vk? Can you see that we are obtaining the eigenvalue right now? Can you appreciate? It might not be that intuitive, but what we just did is take a dot product with the same vector again. And that will result into scalars instead of vector. The previous equation we were dealing with vector. This equation we are dealing with scalar right now. Okay. Can you appreciate what is going through? You will understand it more clearly when we take an example. What should be done next? What should be done next? Any ideas? Any ideas? Hmm? You found eigenvalues, right? So any other step is needed to be done, or this is the step is fine with you? Think about like any other step needs to be done or no. Any more thoughts, or else we'll just go to an example and see what we are trying to do here. Shall we go to an example and see what, so that you can understand it better? So I ask you to see what we have done so far. What is our iteration scheme and how we computed lambda? Okay. So let's begin with an example so that you can appreciate it better. Okay. We'll just start with a minute example so that you can do by hand. Okay. Let us take the same example as we had taken before. We took the same, right? Yes. So I ask you, find the dominant eigenvalue. Find the dominant eigenvalue. Find the dominant eigenvalue. Its corresponding eigenvector. So this is where you can appreciate the method bit more clearly. So first of all, for this method, we will start with an initial guess, isn't it? Of course, that's what our numerical method does every time. So this I will denote by V0 bar, okay, V0 hat, that is the direction vector of, this is the initial guess. Okay, suppose I take the initial guess to be 1, 0. Then I ask you, what is the next iteration vector V1? It will be A into V naught. Yes, A into V naught, right? Is it correct? How many of you think it is correct? Yes. So yeah, A into V naught. But the problem we will run here is, we will get a vector, but we should work with unit vector. So every time you do the power iteration, every step, iteration of the power method every step, it is strongly recommended that every vector you get, you normalize and bring it down to a unit vector. Make it a unit vector. Okay. So how you will make a unit vector? A into V is another vector, right? You agree? Matrix into a vector is another vector, right? Now how you can make it to be a unit vector? Divide divide by the norm. So what you will do here is just divide by the norm of a v0. Just that. And I want you to do this every step. Every step you calculate a new vector, you do this. So can you tell me what is a into v0 and divided by the norm? Can you tell me? Tell me in decimal numbers. Oh no. Okay, 0.75926. Then the next component. Okay, this is the second eigenvector, right? This is the first vector after your initial guess. This is V1, okay? You can confirm, you can take the magnitude of this vector and confirm that magnitude of this vector is 1. Okay? Now I ask you, what is the second iterate? What should it be? Anyone? No, no, what should be the formula first? A into the past vector, that is V1, divided by the norm of the first vector, right? So what is that vector? Tell me. 0.717. Good. Are you sure? Are you sure? Yes. Check your computations. Then, yes. Okay. But before that, if you want to analyze something, then it would be really good. Now I ask you, now you know the method, like the steps. Okay. What I ask you at every step to do is one additional thing. That additional thing is compute the eigenvalues, or compute, it's not eigenvalues, compute some quantity based on a formula. That's it. And that will be your eigenvalue after few iterations. That's the idea. So I told you how to compute eigenvectors, isn't it? Sorry, eigenvalues. How? I just wrote it here. It is this formula over here. Okay. A into Vk dot Vk by Vk dot Vk, right? Fine. Let us use another color. So what I ask you is compute lambda 1 at the same place. Lambda 1 here will be A into V1 vector dot V1 vector. That's it. Divided by V1 into V1. What will be that? That will be just 1. Because V1 is a unit vector and dot product of two unit vectors is again a unit vector. Dot product of two units same vector is again a unit vector. So this guy on the denominator is 1. So lambda 1 is nothing but a V1 into V1. Can you tell me this number? This will be a number, right? Because you are taking dot products. And dot products always return scalar. It never gives you a vector. That's the idea. A V1 into V1. Can you tell me? You had V1 with you. I am asking you, what is A V1 into V1? I will recap this method so that everything will fall in place. But I'm telling you after some steps so that it won't be sudden for you. Like you might not ask that why we are doing this. Okay. Can you compute? Can you compute lambda 1? Just you have to multiply a v1 with v1. V1 you already have, isn't it? A v1 you just have to dot product. Yes. How it can be? It cannot be zero, right? How it can be zero? But this is not an into. This is a dot product. Dot product you know, right? Yeah, that's it. Okay. So now I'll ask you a few basic things. What is a dot product? Dot product, like you have two vectors A bar and B bar. What is the dot product of A dot B? A dot B is equals to, you already know, it's the magnitude of A, magnitude of B into cos of angle between them, right? This is one formula. This is one way of representing the dot product. But what this dot product tells us, if you have two vectors A and B perpendicular to each other, what is the dot product? The dot product will be zero because cos 90 degree will be involved, isn't it? It will be zero. Fine. Okay. But more importantly, there is another way of representing the dot product. Suppose A bar, you already know you can represent using I, J, and K cap. Yes. Suppose A bar is, let me write V1 bar is 3I plus 5J. Yes. And V2 bar is just how much? Maybe I'll start with a good example so that you can appreciate. Maybe why it is not. Let us take 3 I cap and this is 5 5 I cap. Okay, 5 I cap. You can see that both these vectors are in the same direction, isn't it? Now I am asking you what is V1 dot product with V2. So it should be 3 into 5 cos 0, the 0 angle. So it should be 15, right? It's a scalar quantity. Now there is another way also. V1 dot V2 is equals to 3I plus 0 j cap. Fine. Dot with 5I plus 0 j cap. Fine. Now what I ask you to do is take the dot product with individual elements, like that is equal to 3I. Let us take 3I in dot product with 5I plus 3I cap dot product with 0 j cap plus 0 j cap dot product with 5I cap, then 0 j cap dot product with 0 j cap. So what you are getting here, 3I cap dot product with 5I cap is 15, isn't it? Because I cap dot I cap is equal to 1. Why? I cap is a unit vector. I cap is a unit vector, right? So therefore it will be 15 plus 3 I cap dot 0 j cap. What it is? Just 0 plus other quantity as just zeros. Just 15 you got. Fine. Can you see by both methods? By both methods, you can compute the dot product. Now let us return to our problem. Fine. This is the revise of the dot product. Now I ask you, lambda 1 is equals to two vectors, that is 7.26, 7.15. This is the dot product with 0.7592 and 0.6507. Yes, what we should do to take this dot product? You can see that you can write this as 7.26 I cap plus 7.15 j cap, because it's a two-dimensional vector, right? It will be lying on the xy plane, right? 0.7592 I cap plus 0.6507 j cap. Now, can you see what you have to do? You have to just multiply the corresponding elements. So what you have to do? 7.26 I cap with I cap only, because with j cap it will be just 0. So you have to multiply I cap with I cap. So 0.7592 plus 7.15 into 0.6507. Can you tell me what is this value? 10.164. Can you see? This is the only at the first step. The eigenvalue is only at the first step, isn't it? This is for V1, first iteration. You got 10.16. What is your original eigenvalue? 10. You computed the original eigenvalue, right? Before the class, in the beginning of the class, it to be 10, right? So can you see it is making a good approximation? And it is making a good approximation only to the dominant eigenvalue. It is not making an approximation to the lowest eigenvalue, but to the dominant one, to the greatest one. And this is only the first iteration. This is only the first iteration. Can you see what is going to happen in the second iteration? No. Try to see. It will be much closer. Can you do the second iteration? What should be the second iteration? V2, right? V2 should be A multiplied with this A V1. What you get? Tell me. And corresponding to this V2, what should be the lambda 2, the eigenvalue? Lambda 2 should be A V2 dot product with V2, because you will multiply with this dot product, but then this will be unit vector, just one. So it is just same as writing A V2 dot V2. I am saying that you give me V2 in terms of the unit vector. Okay with you? Can you let me know this? Now you can do, because now you know how to compute the dot product and all. Yes, lambda 2 equals to, what is AV1? Sorry, AV2, tell me this quantity and this quantity. AV2. Then yes, I will talk to you after the pause. Wait. 7 point. Okay. Then what is the dot product with V2? V2 is 7 on 4. Okay. So this you got around 10.5. Okay. Can you see the difference now? Previously you were getting 10 point. Yes, previously you were getting 10.164. Now you are getting 10.01. Okay. Can you see that it is slowly approaching to 10? Yes. And 10 is your eigenvalue. 10 is already your eigenvalue which you computed in the beginning of the class. Okay. So I ask you what should be the third iteration. Third iteration V3 is equals to a V2 divided by the norm of the same vector so that it becomes a unit vector, right? After you compute this V3, proceed to compute lambda 3, the third approximation of eigenvalue. That should be equals to A into V3 dot V3. Yes. Yes. So you can see that you start with any random vector that is in blue, V naught. Okay, then what we do, we compute the new iterates of the vector, that is V1. How to compute V1? V1 we compute by multiplying matrix A to V naught. And to make it a unit vector, you just, right? So here I am showing how to compute the next iteration of the vectors. Okay. So how we will do this? You can see V naught is in blue color in this diagram. Okay, in this plot, V naught is in blue color. V1, which you see, is in gray color. V1 is a V naught. V2 is a V1, that is another slightest new gray. And you see, when you do this V3, V4, V5 subsequent iterates of this, creating a new vector, you see that it is converging to a red vector, isn't it? Yes. So that red vector is your eigenvector. That's where your values are converging. That's where your vector is converging. Okay. So you can see that what is your eigenvector here. Red is the eigenvector, and why your power method is actually converging, you can appreciate now. Okay. Anyway, so this is one method I showed. Yeah. And that will be it. But in the next class, when we enter, we will see a graphic visualization of the QR method. Why this QR method actually works. So we can see this via an animation. I'll just show you here that this is how I am representing a matrix using a heat map. Okay, just the values of the matrix you can just see in terms of colors. Okay, and the iterates you will create new matrix. Okay, so new colors. Okay, you will see. So we want to see how this color varies with the iteration. So if I play this video for you, you can see like, yes, after like maybe 10 or 5 or 3 iteration, the color got stagnant, isn't it? So you can appreciate, just see in the middle part of the matrix. Wait. So you can see how the colors were different initially and how it got changed, and it is now a constant color now. Whatever you do, it is a constant color. That means your method already converged. Okay, and you see the method only converged to the diagonal elements. Only the diagonal elements are colored. The off diagonal elements other than diagonal are like no color. Okay, just gray, right? Those will be zeros for you. You will see. So this is basically the QR method we are looking at right now. Okay, the QR method, what it does is it will do some changes, some matrix multiplication in such a way that you will just see these diagonal elements, and these diagonal elements, your colored ones, are just the eigenvalues. Okay, are just the eigenvalues. So you can see red means it will be a value close to 1. Okay, a value it will be close to 1 according to this legend. And blue means it will be close to -1, or maybe it is lighter blue. So you can see this guy over here will be definitely around -0.25 or something. So you can predict the eigenvalues as well. So this is a graphic visualization of QR method. Okay, and this was a graphic visualization of the what you call this is a graphic visualization of the